Now let's start with the definition of current, and current is the rate at which electric charges move through a given area. And again, right away notice it says rate. It says rate. So when you hear rate, you know it's per given time period. So right away we know that this is going to be some sort of a amount of quantity moving in a given time period. So it's electric flow. Think about flow rate of water, like a river. A river has a current as well. This is the electric current. So some examples are machinery, appliances, computers, or like, the veins in the human body. These are obvious ones. This not as much. There's also electric current that's going through the central nervous system of the body. So current in general, but specifically electric flow we're going to talk about. Now the formula here is I equals delta Q over delta T, where delta Q is the change in charge. Okay, the electric charges that move through a given area over a given time period. So it's a rate, given time period. So how many coulombs pass per second over a given cross-sectional area? And the units of current are ampere, abbreviated with capital A, and named after Andre Marie Ampere. Another thing to notice is that this I here in the front comes about because current was originally, in French, phrased intensité de courant, or in English, current intensity. And the phrase is just simplified to be current, but it's current intensity, and the intensity gives the I there in the front. So first remember that with conductors we're really looking at the flow of electrons, but it's also possible for protons to flow. Now, what we're going to think about is that a flow of positive charges, well, that really gives the same electric current and has the same effect in the circuit as an equal flow of negative charges in the opposite direction. So it doesn't really matter which way to think about it. Traditionally we say that the direction of current is opposite the movement of negative charges, and this is just completely arbitrarily defined. So to summarize, remember that in metals, or most things that are made up of wires and other conductors in electric circuits, the positive charges are really immobile, they're not moving. So the charge carries again are the electrons, but because the electrons carry negative charge, the motion of the electrons in a metal conductor is really is the opposite of that of a conventional current. And finally, we could also think of a combination of positive and negative flow, and this can exist. And this happens when you have gases and dissolved salts. So when we're looking at things that have ions in them, so they make the fluid into an electrolyte, and then you can have positive and negative flow through those fluids. But again, we're looking at metals and circuits and conductors. So example 1 says the startup current for a standard refrigerator is around 15 amps, but the running current is around 3 amps. For a 10-second time interval, how much more charge passes a given point in the circuit during the startup mode than in the running mode? So again, here we're now going to look at the value of Q in each of these situations, or delta Q in a sense. So I want to find out what the difference in Q is in this problem. Well, I can think to myself here, I've got a value of I for the starting point, and I've got a value of I for the running current. So I could start by writing the fact that I know my formula is I equals the change in Q over the given time period. So since we're looking for Q here, we're going to have I times delta T equals delta Q. Now, since we're looking for the charge in two different situations, if we do this twice, we could say to ourselves, all right, well, we have I1 times 10 seconds, because the time interval isn't changing, and that's going to equal delta Q1, the change in charge in the first situation, and then we have I2, the running mode of 3 amps, again times 10 seconds, that's going to equal delta Q2. In reality, we're looking for the difference in these two, so we're going to have, again, 15 amps times 10 seconds, or 150 coulombs. How do I know it's coulombs? Because an amp is really a coulomb per second. Here I'm going to have 3 amps times 10 seconds, and that equals delta Q2, so this is a value of 30 coulombs of charge. So what's the difference, or how much more is running? 150 and 30, so 120 coulombs of charge every 10 seconds compared to its starting mode to its running mode. And now this makes sense logically, because think about a refrigerator. When you start it up, the refrigerator is right out of the box. The air inside of it is room temperature. It has to cool down, it has to remove all the heat. So it's going to run at a high current initially, and then once it gets going, once it's cooled down, it's going to maintain that state of equilibrium running at 3 amps and drawing less current. Let's talk about drift velocity now, and drift velocity is the net velocity of a charge carrier moving in an electric field. So this is in the circuit. So let's really take a look and think about the fact that current has to do with the number of coulombs of charge that pass a given point in a circuit in a given period of time. And because of its definition, it's also a lot confused with the idea of drift speed. But drift speed or drift velocity really refers to the distance traveled by the charge carriers per unit time. And like the speed of anything, we're looking at the distance-to-time ratio. So here, the typical path of an electron through a wire could be described as chaotic. It zigzags back and forth with collisions with the metal atoms, and each collision results in a change in the direction. So because of all these changes, it's like every time it goes 5 feet forward, it comes back a little bit, like another 2 feet, or 3 steps forward, 2 back, the idea. Now, when there's a battery connected to this, the electrons continue to migrate and move forward, but they move very slowly. And the overall effect of them is these high-speed collisions, that the drift speed is really, really low. It's typically as low as like a meter every hour. A meter every hour. Think about how slow that value is. In meters per second, some are such as low values of like 2.5 times 10 to the negative 4 meters per second. So we're talking really, really low velocities. Now, you can say to yourself, well, how does this make sense? Like, how can the current be so high if the velocity is so low? Well, the idea again is that current is not really velocity, but it's the rate at which the charge carriers cross on a given point in a circuit. For example, if I had a really, really wide pipe and a lot of water were passing there, it would have a very high volumetric flow rate. That's what this is. It's a volumetric flow rate. In this case, we're looking at the amount of charge carriers or electrons that cross a given cross-section. So if I have a cross-section that's, a really small cross-section, only a few electrons might be able to pass through here or whatever it is, right? But if I have a much larger cross-section, then there are many of these that can carry through here or that can cross in a given time period. So they don't have to be moving fast as long as there are many, many of them moving across a given area in a given time period. That's what current really is. It's not really the speed, but it's how many move across a given area in a time period. And again, this cross-section of the wire here indicates or shows how this works differently. The current here is much higher than this current, for sure. To give another analogy, suppose there was like a really large race with a ton of really, really slow turtles running. And say the race was only like a meter in length. And there were like 10,000 turtles on the starting line. And after 30 minutes, a lot of the turtles reached the starting line. Well, this would have a really, really, really low drift velocity because, again, they're not really traveling with a high velocity, but the current would be very large because the turtles are like the charge carriers. There's a lot of turtles in that short time period that are passing that given point. So in this analogy, again, we're talking about how many turtles cross the finish line at the same time or in that certain amount of time that we're looking at. Now, the next real question is, well, why isn't there a delay when you turn a switch on, but it immediately turns on, right? Wouldn't there be a noticeable quick delay there? And the answer is no, there's not. And the explanation has to do about what's called a charge carrier, as we've been saying. So charge carriers in wires, they're electrons. And the electrons, they're just supplied by the atoms of copper or whatever the material is made of in the wire. And once the switch is turned on, the circuit's then closed. And what this really means is that there's a battery that's connected, or a potential difference, a high potential and a low potential, a positive end and a negative end. That's why we talk about the potential difference. And the circuit signals this electric field, and it travels at the speed of light, and it tells all the electrons in the circuit to start moving. So they all start moving at this low drift velocity, but they all start moving at the same time. It's like a bunch of soldiers in line, and they hear the order, like forward march, and they all start marching at the exact same time. So as soon as the electric field, which itself travels at nearly the speed of light, tells them all to do that, they all start moving instantly. Well, remember, it's not like electrons are like really moving throughout there. The electrons are already in the copper wire, in the filament, in the light bulb. So inside the light bulb, the charge carriers, they're already there. They just have to start moving and carrying that charge, actually. So the light bulb begins to light, and the charge carriers begin to move, but at a very slow rate, but they feel that instantly because the electric field tells them that almost instantly. Another analogy is to think about like your pipes in your house. When you turn the faucet on, the water immediately comes out of the spigot. It doesn't like wait, there's no delay or anything like that, because you have to think about the fact that the pipes, they're already filled with water. And as soon as you turn the pressure on, all the water starts to move together. Well, these circuits, they're already filled with electrons, and the electrons just begin to move through the wire. They move from atom to atom, the electrons just keep carrying. So they keep moving, and when the electrons that were in the filament originally all end up leaving, because they eventually will leave that filament, other ones take its place from the wiring that was existing there. So the electrons are just moving from piece to piece. So we're going to look at two sources of current that generate current, and the first example are batteries, and batteries convert chemical energy into electrical energy. So you're looking at a battery that has an anode and a cathode, and that anode and cathode create a potential difference, and the current is carried throughout there. The second is a generator, and a generator converts mechanical energy to electrical energy itself. And examples of this are like hand cranks, a dam, a steam engine, or a combustion engine, a wind turbine, a lot of different examples there. Now, a generator is not to be confused with a motor. A motor takes electrical energy, converts it into mechanical. So here we're looking at a generator, and a generator has some mechanical input. And the example here is a simple generator inside of a magnet creating that current that powers that light bulb at the end there and the electrical output. So now let's take a look at the difference between direct and alternating current. A direct current is when a charge moves only in one direction in the circuit, where like for example, battery whose terminals are fixed. Other examples are things like solar cells or thermocouples, they're fixed. So the direction of the circuit only continues in one direction. And what we'll notice is that the current is a constant, right? We're seeing the current value does not change. That's what direct means, or fixed. It's also good to know that direct current used to be called galvanic current. Now, AC current, or alternating current, is the motion of the charges that they continuously change between forward and reverse. And the idea is like a generator whose terminals are changing. So think about a positive and negative end of a battery. The electrons are going to want to flow toward the positive end, right? But then imagine if that end kept switching. The electrons are going to go back, then forth, then back, then forth, then back, then forth. The idea of alternating. Electrons are going back and forth like this. So there's really no net motion of the charge carriers. They're kind of like staying still, but they're just going like this, back and forth, and vibrating at really high frequencies. Now, if the vibrations, if they were slow enough, somebody would actually notice this. For example, in like flickering of lights or other appliances. The frequency in the US of alternating current is 60 hertz. And this is a good frequency because we don't really see that flickering. So resistance is defined as the opposition to flow of a current in a conductor. Well, it's the same idea as thinking about a flow of a current in a stream. What would oppose the flow? Maybe if there was like, a bunch of beavers that built a dam at the end of the little stream, well, that would oppose the flow. That dam would be a resistor in a sense. And there are several things that affect resistance, and we're going to talk about those in a little bit. The second definition we have to make is called voltage, and voltage is really defined as a potential difference. And this happens when a positive charge flows through a circuit, and each coulomb of charge gains some amount of potential energy as it flows through the circuit in joules, and we're looking really at the ratio of energy gain per coulomb. Okay, remembering that a voltage source or a battery has two nodes, a positive and a negative node, thus creating the potential difference between them, enabling the positive flow to actually go through the circuit. Ohm's law tells us that the voltage is equal to the current times the resistance, and this is across any individual element in a circuit. So if you wanted to figure out what the resistance was of a certain material, say a light bulb, how much does it slow down the flow of the current, you could simply determine the voltage drop across the light bulb, and you could do that experimentally using like a voltmeter. You could figure out what the current is that you're providing for it, and you can figure out as a result what the resistance is. So traditionally, this formula can be thought of as resistance is really equal to the ratio of the voltage drop across that element to the current flowing through that element. Now, just so we're clear about units, voltage is measured in volts, current is measured in amps, but resistance is measured in ohms. And this is the symbol, okay, for omega. So if you had this symbol here, this is the symbol representing your resistance. Here's your amps, and here's your volts. Now remember, if we take a look here, we'll notice that we're talking about resistance really, and a lot of
elements have a constant internal resistance. So say a light bulb had a resistance of 20 ohms, and you had a certain current going through it, you could figure out the voltage. But let's say we had some constant value here, right? So it's an object that doesn't change resistance. And what you'll notice is that if you double the current supplied, it will double the voltage across that resistor. If you triple the current, it will triple the voltage. Because these two things, again, you can see here, they are directly related looking at it this way. Or we could say that in order for this to be the same number, say this number is 5. Say the resistance is 5 ohms. The only way to get 5 ohms in the denominator, if we have, like, say we have, I don't know, 7 down here, well, this has to be 35. But if that 7 doubles, if that 7 became, say the current became 14, well, then this has to be 70, because 70 over 14 is 5. So traditionally, we're looking at things that have constant resistances, and we'll see that again. The definition of resistance we can think of as the ratio of voltage to current. Now, Ohm's law, it's not really a fundamental nature of law, okay, but it only works for certain materials. And materials that Ohm's law holds true for are called to be ohmic materials, and they have a constant R value, meaning the slope of the graph below here we can see is constant. And we'll notice this because we're plotting the current versus the voltage, or the potential difference. Well, this is your I, right? This is your voltage here. So if we recall the formula we had from the last slide, resistance is really equal to voltage over the current. Well, we're going to see here that this graph is simply plotting the inverse of that, right? It's plotting the current versus the voltage as opposed to the voltage over the current. So what you'll notice is that the slope here, instead of the slope becoming R, the slope is just 1 over R, because these are the inverses, right? These are flipped around. This is taking the current over the voltage, whereas we had the voltage over the current. So, but still, if R is a constant value, then 1 over R is also a constant value. If this is a number like 5 ohms, then the slope of this line would be 1/5, right? 1 over R. But the idea that the slope is constant, it's a linear function, tells us that it is ohmic. If something were non-ohmic, meaning that the resistance is not a constant, we'll notice in the graph here that there's a curve to the graph. Okay, as the potential difference increases, the current increases, but not necessarily linearly, not in a linear fashion like it did before. So this curve here tells us that it is non-ohmic, just saying that the function here is not linear, right? Not linear. And the reason we can tell that, remember, here was our original formula, V equals IR. Well, this is thought of as, in this graph at least, R is thought of as almost like your slope, okay? If R is constant, the slope should be constant. This is like your dependent, and this is your independent. The graphs here, these examples, happen to switch those two. They plot current versus potential difference. Now let's take a look at 4 factors that affect resistance. And first of all, remember that resistance is really a collision or result of more collisions between electrons and the metallic atoms in the copper wire, whatever the wire is made of. So the first thing we'll notice is that length is directly related. Shorter length, less resistance. Longer length, more resistance. And this makes sense. Think about a longer strand of wire. It simply means that there's going to be more chance for this electron to bounce around. We think about drift velocity whenever we think about that. The electron really is not sitting still, but it's kind of bouncing around, pinballing back and forth in here until it gets to the other end as it moves. The second thing we'll notice is that cross-sectional area is inversely related. Again, higher cross-sectional area, lower resistance. Smaller cross-sectional area, more resistance. And let's think about this for a moment. Well, here it's clear because, look, this is like a pipe when water's flowing through a pipe. Water can flow through this pipe a lot easier than water flowing through this pipe, especially if there's an abundance of water. Here, if you had a lot of water, it might get backed up. It's like having 4 pipe drains coming into one in your house. You'd want the big pipe drain running out to the ground and all the other pipes to be smaller so that when they come together, they could actually flow out. Whereas if you had 10 pipes that are 1 inch or 2 each, and then you had an exit pipe that was only a 1 inch diameter, it's going to get all backed up. All your water's going to get backed up in your sink and your shower, and it's not going to actually flow out. So a larger pipe means less resistance. So think about with water, okay, water flowing through a pipe. So same thing with the current here. Less resistance in the current, more resistance in the current. The third thing we're going to look at is the material, and we're going to look at different materials in general, but just to make it easy for us, we're giving 2 examples here. We're looking at copper and we're looking at iron. And copper has less resistance than iron does. And there are several materials, actually there's only one that I know of that's a natural material that has less resistance than copper, and that is silver. But because silver is so expensive, you wouldn't be using silver for wiring, you would end up using copper. The fourth thing to look at is temperature. And we'll see here that there's a low temperature, and up here there's a higher temperature. So we'll see that this is directly related also. As temperature goes from this, whatever this value is, to a larger value over here, we get greater resistance. So low temperature, low resistance, high temperature, high resistance, directly related. Example 1 says that the resistance of an air conditioner is 21 ohms. What is the current in the air conditioner when it is connected across a potential difference of 115 volts? So here's like your battery source. We're going to see that later on in our circuit unit. And this is the overall resistance of the air conditioner. And obviously the air conditioner is made up of many components, each with their own individual resistances. But we're looking at the overall net resistance of an air conditioning unit. So here we have a voltage of 115 volts. We've got a resistance of 21 ohms. And we're trying to find the current through this air conditioner, or across the air conditioner. How many coulombs per second are flowing through this air conditioner. So we've got Ohm's law telling us V equals IR. We're solving for I, so I is equal to V over R. The current is equal to the voltage over the resistance. So we take 115 volts over 21 ohms, giving us a current of approximately 5.5 amps. Remembering, please, that amps are really coulombs per second. So what this really means is that we've got 5.5 coulombs per second passing a given point in the air conditioner. So 5.5 coulombs of charge pass a certain location every single second. And you can think of this in terms of electrons. You could say, well, how many electrons is that really? Well, if we know that there's 1.6 times 10 to the negative 19 coulombs in every electron, right? That's so many coulombs of charge, and this would be a negative charge for coulombs. Well, we could go ahead and take this number and divide it by this number here, and that'll give us the amount of electrons that are passing that given location every single second. Next, let's talk about a potentiometer. And a potentiometer is related to this topic because it's a special type of resistor. And the way it works is it has a sliding contact that changes the actual resistance in it. So for example, you walk in a room, you can turn the light switch on or off. Sure, you're opening or closing the circuit. But a light dimmer adjusts the amount of flow by changing the resistance with a metal sliding contact. A volume control, changing the decibel level, or a joystick on a game controller. Okay, a joystick on a video game controller would have altering signals sent to it. So if you push to the right more, the character in the game might turn right very quick as opposed to turning to the right lightly, and they might be panning to the right very slowly. Finally, the last thing we want to look at are superconductors and their resistance. And we mentioned this earlier already in another topic, but let's specifically talk about it now. And a superconductor, again, exhibits zero resistance below a critical temperature. So for example, this graph is showing us that there is constant resistance as the temperature increases. It increases at a constant rate. Right? Temperature goes, here's the temperature. Temperature goes up, the resistance goes up. But below a certain point, it drops dramatically. And then we have something called a critical temperature. At every temperature below this, in this case it'd be 4.15 kelvins. Okay, every temperature below this, the material exhibits zero resistance or negligible resistance. And what would happen here theoretically would be if you applied a sudden voltage to a circuit, it would continue forever and ever. If that wire were cooled enough, nothing would ever stop that current from flowing around. It'd be like a frictionless surface. That's what this really is. There's very, very little resistance or little friction stopping it.